Okay, and the next thing is a directed acyclic graph. And directed acyclic graph is a finite directed graph with no directed cycles. The direct acyclic graph is a directed graph that has a topological ordering, a sequence of the vertices such that every edge is directed from earlier to later in the sequence. I want to pay attention on the directed acyclic graph because next algorithm is totally based on this type of the graph. So it means in this graph, in this type of the graph, there is no cycle, and the graph is acyclic, is directed. So each edge has direction. So here is example of the deck. So here you see that every edge has direction, and there is no cycle. So if you start to go from the A, and there is no way to go back to the A with different paths. For example, if you want to go to B, then you go to the D, then you go to the C, and that's it. There's no go back. There's no way back to the A. Okay. So directed acyclic graph can represent many things in real life. For example, prerequisite of the classes. As you know, in order there are like many classes that you can take, and in order to take some classes, you need to finish some other classes. For example, let's say that you want to take the programming of object-oriented programming, and in order to take object-oriented programming, you need to take the programming classes, right? So one class depends on other. Next is event scheduling. In the event scheduling, when you plan some events, in order to do some events, you need to do before other events. For example, Kazakh weddings. In a Kazakh weddings usually consist of the two parts, right? First part is called Kosaraju, and second part is the wedding itself. And usually the Kosaraju should be before the the wedding itself. There is no other way. So also, and there are many other events that need to be scheduled, and in order to represent that events, the directed acyclic graph can be used. Next is assembly's instructions. So let's say that you get some let's say bike, and the bike comes to you in the pieces, in the details. In order to assemble that bike, you need to read the instructions, and in that instructions you need to assemble the details one after another, and the specifics and the orderings of the assembling is very important, right? And one important thing that about assembling that there is no loop. For example, when you assemble, you don't assemble that thing again, like you don't do a circle like cycles. And in order, for example, assemble some wheels, you need to do like assemble something before other details before that. Next, also it's a program dependency. It's like when you um, write some software, you need to do some function before the other, and it's all dependent on each other, and the ordering is very important. You need to like do one functions, you need to write one features before the others in order to complete, and there is no other way, and there is no need to like go make cycles, and these all things can be represented as a direct acyclic graphs. Next is I want to talk about the topological sort, and the topological sort is works only for the direct acyclic graph. So topological sort is a linear ordering of vertices such that for every directed edge UV, vertex U comes before V in the ordering. Topological sorting for graph is not possible if the graph is not a direct acyclic graph. So topological sort works only for direct acyclic graph, and one graph can have many topological orderings. So the result can be not always one only. You can, for the one graph, there are like many ways of the sorting is possible. And the time complexity of the sorting is big O V plus E. So how does it work? So let's say that we have this directed acyclic graph, as you can see here, and after the sorting, it says that if you have H, A, and H, after the sorting, A will be always before the H. So here there is H that goes from the C to the D and E, and after the sorting, C will be always before the D and E. And here is the B. B will be always before the D. And for the D, D will be always before the F and H because there is outgoing edges from D to F and G. So after the sorting, we could have this kind of topological sort. So C always before the D and E, as you can see. B also is before the D, and A is before E, right, and H. This is the first version of the topological sorting. The second version can be something like this. So before first stays A, then stays B, then C, E, D, H, G, F. But one rule is very important, that if there is H that goes from one vertex, let's say A, and goes to another, this vertex will be always before this vertex, whatever the ordering will be in topological sorting. So in order to have topological sorting, the graph must not contain any cycles, right? And how can we prove that it works only in a cyclic graph? So we can prove that by contradiction. So let's assume that there is a cycle made of the vertices v1, v2, v3, and vn, right? So let's say that there is some graph, and in the graph there is a cycle which is made of these vertices, and it means that there is a directed edge between vi and vi plus 1, and between vn and between v1. So if we do topological sorting, then vn must come before the v1, right? But because of the directed edge from vn to v1, but v1 should be before the vn, because vi plus 1 will come after vi, right? And the vi comes after the v1, and but v1 already is comes after the vn, so it's not possible to do. So there is a contradiction, so it's not possible to do topological sorts on a cyclic graph. So we can use Kahn's algorithm to do topological sort. So what is the Kahn algorithm? Kahn algorithm says that a direct acyclic graph G has at least one vertex within degree 0 and one vertex without degree 0. So in order to do Kahn's algorithm, we can build any graph using any graph data structure, and then we create the queue, and we need to run through all the vertices of graph and enqueue all the nodes that have in degree 0. So we start to put into the queue all the vertices that has in degree 0. So if we go back, the graph, the vertex that has in degree 0 is this one, B and A. So we put these vertices into the queue, right? Because they have 0 in degree. Then we run another loop, and we start to go through the queue and popping off the top. The top node is the current node, and from that node we take all the neighboring elements of that node. So here, for example, we take from the queue A, and we take the all neighboring elements that is a neighbor for the A. So it's E and H. So we remove A from the queue, and we decrease the in degree of the E and for the H. So we degree. So before that, the in degree for the E was 2, right? And for H, it was also 2. We decrease it by 1, so the in degree becomes 1 here, right? So we remove this kind of edge, and we remove A from the queue. Then we take the next element from the queue, which is let's say B. We remove the B from the queue, and we decrease the we kind of remove the edge that is connected to the B. So we decrease the in degree for the neighboring element for the B, which is a D. So we remove this, and this one becomes the in degree of D becomes 1. Then we take out the C from the Q, and also we decrease the in degrees of all nodes that is connected from the C. So we remove C, and the in degree of 0 becomes 0. Oh, the in degree of the D becomes 0. So we put D into the Q. Then we decrease E, and E's also becomes 0, right? So we add into the Q D and E. So in our Q we have two elements D and E. Then we, let's say, take E, and we decrease the in degree that is connected from the E. So for G we decrease it from the 2. So here you see 2 in degrees incoming edges. So we decrease it to the 1, and we remove the E from the Q. Then next we take the D, and from the D we also decrease all the connect nodes, so it's 0. Here it becomes 0, and also this one becomes 0, and we remove D. So in the end we have FGH, and we just remove the FGH from the Q because it doesn't have any adjacent vertices, and the order of extracting the elements from the Q is actually the ordering of the topological sort. So, and one good thing about the Kahn's algorithm is that Kahn's algorithm helps to check is the graph directed acyclic or not. If the graph is directed acyclic, in the end, in the Q, we will not have any elements, like in a graph, we will not have any elements with in degree more than the 0. So for the direct acyclic graph, after the Kahn's algorithm, every vertex will have in degree 0. So time complexity of Kahn algorithm, initialization of in degrees to 0 will be executed v number of times. The inner loop will be executed for each edge is e number of times. And each node is we put into the key exactly once. And is it dq, the degree is reduced for all its edges. So the overall time complexity is big O of v plus e. Why it's working? So let's say there is a cycle v1, v2, v3. So at each step of the algorithm, none of the v1, v2, vk is a source, proving it by induction by showing you never remove any of these edges. So let's say that G doesn't contain a cycle. All the paths in G are of the finite length. And let's say that we have two vertices and like two vertices, and it is let's say that S is the longest path from U and V. So U will be the source and V will be destination. Since S is the longest path, there can be no incoming edge to U and no outgoing edge from the V. So if we have the longest path S from the U to the V, and it means that to the U we don't have any incoming edge, because if it has incoming edge to the U, it means that S is not the longest path. It can be even longer path, right? And if there is outgoing H to V, it means S is not longest path because V has like next continuous vertex, and S is not the longest path. So if the above situation had occurred, then S wouldn't have been the longest path. So this is a contradiction. Next, I would like to talk about the graph connectivity. So connectivity in graph means that every vertex can reach every other vertex via any path. If the graph is not connected, the graph can be broken into the connected components. So here is the graph, and the gray colored areas are the strongly connected components. It means that every node, every vertex has a path to other vertex in a component. So, for example, in A, for this vertex, you can reach this vertex, you can reach this vertex, and you can reach this vertex, and vice versa. Any other vertex can reach any other vertices. And if, for example, there can be some component which can consist of only one vertex, because for this one, it can reach this vertex, but this vertex cannot reach this one. That's why this node itself is the only element of the strong component, connected component C, right? So in order to find the strongly connected components, there are two main algorithms. Its first one is the Kosaraju algorithm, and second one is the Tarjan algorithm. So what is the Kosaraju algorithm? Kosaraju algorithm is a linear time algorithm to find the strongly connected components of directed graph. Actually, many people suggested this algorithm before the Kosaraju, so it's Hopford, Ullman. They credited to the Kosaraju Mikhail Sharir, but Kosaraju suggested it in 1978, but didn't publish it, while Sharir independently discovered and published it in 1981. But the algorithm was named after the Kosaraju because he, even though he didn't publish it, he suggested it earlier than Sharir. Um, and this algorithm makes use of the fact that the transpose graph with the same number graph with direction of every each reversed has exactly the same strongly connected components as original graph. So here transpose means that if we reverse the direction of each edge, then if we reverse the direction of each edge, the strongly connected components will be the same as the original graph. So there is no difference. And the time complexity of this algorithm is V plus E. So what do we do? So we do DFS, and we create the stack, and we put into the stack the vertices according its finish time. So if you remember about the DFS, in DFS we can have like discovery time and finish time, and this takes time complexity of V plus E. Then we transpose the graph, so we change the directions of each edge, and it also takes V plus E time, and we do the DFS again and extract vertices from the stack, and it takes also V plus E, and the overall time complexity is V plus E. These three steps are like independent to each other, that's why the time complexity, overall time complexity is V plus E. Next, so in more details, let's talk about in more details about the Kosaraju algorithm. So first we create the empty stack, then we create the hash map for checking all the visited vertices, then we create hash map for checking discovery finish time, then we do DFS on graph and keep track of the discovery and finish time. So when we are done exploring the current vertex, we put it into the stack, then we reverse the graph. Reverse means that we reverse the direction of the graph. Then we do DFS on the graph again with extracting vertices from the stack, and we create the strongly connected component from the graph. So let's say that we have this kind of directed acyclic graph, and as you can see from the graph, these three elements, they are strongly connected components. So this one and this one, right? So we start, let's say that we start from 0, and we have two choices from 0. So it's 2 and 3. Let's say that we go to the 2. Then, so we are doing DFS actually. We start from 0, then we do DFS, and DFS goes to the 2, from 2 to the 1, right? Then it goes back to the 0, but 0 is already discovered, so we put 1 into the stack. So let's say this is a stack. Then we go, so if you remember in DFS backtracking the elements. So when we finish with the 1, we go back to the 2, and from 2 we don't have any other neighboring elements, so we put 2 into the stack. So our stack becomes like this. Then we go back to the 0, and from 0 the edge that goes to the 3, so we go to the 3, from 3 we go to the 4, and from the 4 we don't have any neighboring elements, so we put 4 into the stack. Then we backtrack to the 3, from 3 we don't have any elements also neighboring, and we put 3 into the stack, right? Then we go back to 0, and 0 doesn't have any other undiscovered neighboring elements. That's why we are done. So, and we put 0 here into the top of our stack. Then on the next step of the Kosaraju algorithm, we transpose, so we like reverse the graph. So we change the direction, like so initially the edge goes to this, but we make it like this. So we remove this one, then this edge goes in this direction, right? So we remove this one. Then this graph also change its direction to 0. So we like remove this one. Same for this one, right? And same for this one. So after the transposing the graph, we start to extract the elements from the stack and start to discover the strongly connected components. So we start from 0. From 0, as you can see, there's only one edge that goes from 0. So it goes to the 1, right? So from the 1, it goes to the 2. From 2, it goes to 0. So we go back to 0. So that's it, means that we visit it. So because we go back to 0, it means that this 0, 1, 2, 0, 1, 2, they are like strongly connected component. So we remove 0, right? Then we extract 3, and from 3 there is only one outgoing edge which goes to the 0, but we already discovered 0 here. So, and from the 3 there is no other outgoing edge, and that's why the 3 by itself will be strongly connected component. So we remove 3 from the stack, right? Then we have 4. From the 4 there is only one outgoing edge that goes to 3, but we already discovered 3, so, and there is no other neighboring elements for the 4, so we are done with exploring 4, and so 4 is itself strongly connected component. So we remove 4 from the stack. Then on the stack we have 2, but we already discovered 2, right? So we just remove the 2 from the stack. Then we have 1, and 1 we already discovered, so we remove 1 from the stack, and that's it. So our stack is empty. So this is how we find the strongly connected components. So here is the step by step. So in overall, we can say that after doing DFS, we'll have this kind of stack. So stack will be like this, right? Then we transpose the graph, and we extract nodes and from the stack and do DFS on the graph. Next algorithm, also which finds strongly connected components, is the Tarjan algorithm. Tarjan algorithm is the algorithm in graph theory for finding the strongly connected components of directed graph. Tarjan's algorithm is named for its inventor Robert Tarjan, and the overall time complexity is V plus E. Okay. So how does what does the Tarjan algorithm do? So we do DFS on a graph, then we keep track of the discovery time. Then if node is visited it's in our stack, we compare the tracking time and get the lowest time. Then we move back to the initial node while removing the nodes from the stack and start doing the same process on other node. So let's say that we have this kind of directed acyclic graph, and no, actually we have this kind of directed graph, and we need to find strongly connected components. Let's say that we start from this node, and let's say that we have some like tracking time, global tracking time, which starts, let's say, from 0. So we give 0 this one, and from this node we have outgoing edge to this one, right? Let's say it's 1, because it's we give the time 1, then goes to this one, it's 2, right? Then from this one we go back again to this, but we have already discovered that, and we take the finish time of this node, so we remove 2 and write 0. And we again, because we are doing DFS is backtracking algorithm, that's why from this one we go to this one, and this node has the 0 as finish time, and we remove this one with the 0, and this one is and again we go back to 0, but we already discovered that, so this one is one strongly connected component. Okay, and next let's take another node. Let's take this one. Our time stopped at 2, so we continue here, right? So from 3 we have 2 nodes. One goes to this one, and second node goes to this one. Let's say that we go to this one, so discover time is 4. Then from this one we go here, 5, right? But here we cannot go to this one because we already discovered it. Then we go to this, 6, and from 6 it has 3 outgoing edges, which goes to this one goes to this one, but we already discovered that, one goes to this, but we already also discovered. Then we go back to this one, and 4 it's not finished to discover, so we take this time and we write the 4 here instead of 6. Then again, because DFS do backtracking, we go back to this node, and it is 4, right? From this one we come again here to this, but it's 4, so we are done actually. Let me draw with other color. So let's say this one is the other node, other strongly connected components, right? Then we do the backtracking. It's 3. From 3 we have another node, that is this one. Let's say our finish time finished at our time tracker finished at 6. Then we here write 7, right? From the 7, let me draw with other color. Let's say 7. From 7 we have outgoing edge to this one, but it's already a different strongly connected component. Then we go back to this one. It is 3, so we take 3 and we rewrite this one, and so we go back and we again meet 3, so this is another strongly connected component. So we have the 3 strongly connected components as like here. Okay, so here is the implementation. We initially say that unvisited is -1, and please pay attention to this part of the pseudocode. Here we say that every vertex is unvisited, then run another for loop and say if the vertex is unvisited, we do the DFS, and in the end we just return the lowest finish time, and that's it. Okay, so guys, that's it of lecture of week 6, and the readings are these chapters from the Introduction to Algorithm book. It's 22.1, 22.3, and 22.4. Okay, so that's it, guys. Thank you very much for your attention. See you.